Simplification, or fitting the process into understandable and manageable concepts, is an essential part of math, in which derivatives have a special place. Suppose we have a function f of t, and we want to approximate it at a given point t0. Taylor series is a convenient way to get a polynomial approximation using derivatives at t0. The coefficients of the polynomial are calculated from derivatives of the corresponding order. Generally, approximation gets better as number of polynomial terms increases. However, a few-term approximation is also practical and may help to solve otherwise unsolvable problems. Taylor series are widely used in physics and computer science, mainly because polynomials are functions that are easy to deal with. But what if, at a given point, we want to have a frequency-related approximation? Can we use sines and cosines instead of polynomials? Can we have something like Fourier series that is local and fits the derivatives like Taylor series does? It would be nice to have such approximation for many reasons, especially for functions that are interpretable in terms of time and frequency. Fortunately, thanks to Prony's method, such alternative does exist. It is exponential approximation of a function from its derivatives at a given point. It is also practical with just a few terms as well as Taylor series, and also becomes more accurate as number of terms increases. The nice thing is that this approximation approach offers a considerable representation flexibility. For instance, we can constrain the approximation to be strictly periodical to fit the given period t capital. In this part of the video, we will go through the beautiful calculus behind exponential fitting. We will review the basics and then consider some application examples. Let us start with a quick overview of the exponential parameters and their meaning. To make things simple, we assume that t0 equals 0 and consider only one term. So now we have a single exponential with two complex parameters, h and d. H is called complex amplitude and corresponds to the starting point when t equals 0. At this point, z disappears from the expression, and we have just vector h of length a, rotated by angle theta. As t increases, z amplifies and rotates h with damping parameter alpha and angular frequency omega. The angular frequency omega can be thought of as rotational angle when t has changed from 0 to 1. If alpha equals 0, no damping or amplification occurs, and z just rotates h around the origin. For negative alpha, amplitude exponentially decreases, and for positive alpha, exponentially increases. These two complex points at t equals 0 and 1 define a unique pair h and z, which can be separated into four real values: a, theta, omega, and alpha. If we add one more term, it will require 4 points to define all parameters. And for any non-trivial sequence of 4 points, there will be one unique function connecting them in specified order. Note that we choose equidistant points at integer t that differ by 1. That gives nice usable exponents for z and makes everything simpler. But how exactly can we identify h and z from a given point sequence? Suppose at first that we have only 2 points at t equals 0 and 1. In this case, we can derive a simple system of two equations. z1 to the power 0 and 1 multiplied by h1 equals to f of 0 and 1. So we have two equations and two unknowns that generally leads to a unique solution. This system is easily scaled in the following way. For 4 points, there will be one more column for z2, one more row for h2, and the power sequence of each z will contain 4 elements. For any even number of points, we get a system with 2n equations that yields 2n parameters for n exponential terms. The system is nonlinear and looks quite complicated to solve. Prony's remarkable achievement is that he found a nice solution to the system, which we're going to speak about next. The non-obvious fact that makes this solution possible is that z parameters can be found separately from h parameters. Why is it so? We will try to figure it out. As always, at first we will consider a one-term function, assuming that it equals to h1 multiplied by z1 to the power t. If you write its values at integer t as a sequence, we can notice that each value is its previous value multiplied by z1. So, given two neighboring points, we can evaluate z1 regardless of h1, dividing the next point by the previous. We also can put it another way. Subtracting the next point from the previous multiplied by z1 always gives 0. We can write this as vector multiplication using sequence z1 minus 1. Sequences of this kind we will call predictors, meaning they eliminate exponential terms by predicting their values from the previous points. Now we will move on to a general case, when the function f of t has n exponential terms instead of 1. Let us take two neighboring points of the function and see what happens if we apply this z1 predictor. The first point we will take at t equals k, where k can be any integer number, and the second at t equals k plus 1. We will write the one term separately for both points and simplify the expression. Finally, we have the first term z1 eliminated completely. The rest of the terms have changed their complex amplitudes, but beside that remain the same. So it takes us to the important conclusion that if we know z1, we can remove the corresponding term z1h1 from a given sequence of points, regardless of h1, using predictor of the first order. We have talked about the first term z1h1, but it is clear that this also applies to any other term, because the order of terms is not important. So if f of t is a sum of n exponentials, and we have its points at integer t, we can apply predictor z1 to exclude the first term from all the points. The resulting sequence will be a sum of all the rest terms with changed complex amplitudes h. Then we can apply the second predictor, z2, and it will exclude the second term regardless of changed complex amplitudes. We can repeat this process n times until eventually the last predictor zn turns the sequence into zeros. Mathematically, applying n predictors of the first order is the same as applying a single predictor of the nth order. When we applied each short predictor, we did a convolution, so we can express this long predictor sequence as convolution of all short predictors. It is interesting that we also can make inverse transformation. We can get the original set of n short predictors from the long predictor. When we do ordinary product of two polynomials, we actually do convolution of sequences of their coefficients. So we can write polynomials of variable z with coefficients of predictors. And notice that the short predictors give the same polynomial as the long predictor in factored form. This means that we can identify all parameters z as roots of the polynomial with coefficients of the long predictor. Taking advantage of this fact, we can outline the Prony's solution in the following way. Given a sequence of 2n complex points, at first we find n order predictor solving the following system of linear equations. The system derivation is straightforward and directly stems from the notion of the predictor. Each row of n points multiplied by column of the predictor coefficients should be equal to the next point with inverse sign. Calculating roots of the polynomial a of z with coefficients of the predictors gives n complex parameters z. Each of these parameters can be separated into damping parameter alpha and frequency omega. Using calculated z's, we can solve initial system of equations with respect to h, and then separate h into initial amplitude a and phase theta. Original Prony's method requires equidistant points of a function in order to identify exponential parameters. So we need to discretize the function first, and then apply the method to the discrete sequence of samples. The number of samples should be the number of exponential terms multiplied by 2. If the function is real-valued, the method gives complex conjugate exponential terms that can be treated as damped sinusoids. Each sinusoid requires 4 samples for identification. In this way, the number of samples should be the number of sinusoids multiplied by 4. But is it a good idea to approximate a function at a given point using equidistant discrete samples? Except special cases, when the function is a finite sum of a complex exponentials, actually this might be not a good idea. The method can be inaccurate at the given point because it does not consider derivatives. However, there is a clever trick that fixes that, and we are going to speak about it in a minute. The main idea of the trick is to apply Prony's method not to the sequence of values of the function, but to the sequence of its derivatives instead. If a function f of t is a sum of exponential terms, the sequence of its derivatives at point t0 can be treated also as a sum of exponential terms sampled at equidistant points as required by Prony's method. Let us find a derivative of arbitrary order k of a sum of exponential terms at point t0. Considering that z equals to e to the power alpha plus j omega, we get additional factor alpha plus j omega to the power k. Since t equals t0, z equals 1 and disappears. And finally, we have h multiplied by a complex number s to the power k, where s equals to alpha plus j omega. So the sequence of derivatives for k equals 0, 1, 2 and so on can be treated as a sampled sum of exponential terms h multiplied by s to the k. And therefore, we can apply Prony's method in its original form to the sequence of derivatives with the only difference that instead of z we get s. It should be separated into damping factor and frequency as real and imaginary parts, respectively. Applying Prony's method to the sequence of derivatives, we'll call Prony expansion about a point, meaning that is somewhat similar to the Taylor expansion. Let us have a look at how parameters z and s compare to each other. Z belongs to discrete domain. Discretized sequence is always band-limited, and therefore, on z-plane, frequency omega is limited by -pi and pi. On the contrary, on s-plane, we see that frequency omega is not limited by any bounds. This is one of the reasons why applying original Prony's method to approximate a function at a given point generally is not a good idea. Original Prony's method inevitably will lead to band limiting of the approximation. This example shows how Taylor and Prony expansions compare to each other on the same nonlinear real-valued functions. In case you need to program Prony expansion, you may find helpful a link to Matlab code in the description below. Now let us consider another example and approximate the solution of simple pendulum equation. The motion of the pendulum is defined as function theta of time, which is the angle that pendulum makes with the vertical. The function is given as a differential equation. Its acceleration equals to minus g divided by L multiplied by sine of theta. L is length of the pendulum and g is gravity. Being released at some initial angle, the pendulum will permanently swing around the bottom of its arc. Initial conditions are the angle, theta 0, and angular frequency, theta dot 0. Let us consider the small angle approximation, which is obtained by assuming that sine of theta equals theta according to Taylor approximation. When starting angle is 0, the solution becomes theta dot 0 square root of L over g multiplied by sine of square root of g divided by L multiplied by t. If the starting angular velocity is 0, the solution is theta 0 multiplied by cosine of square root of g over L multiplied by t. We will not derive this solution here, not the equation itself. There are a lot of great videos on this subject. Links to some of them we give in the description. Let us just remember these expressions and move on to solving the equation using Prony expansion. We will assume that the solution is in the form of damped sinusoid. As we already know, in order to identify 4 parameters of one damped sinusoid, we need 4 real values, the value of the function and 3 derivatives. So we get one more derivative. Now we will derive a general solution for one damped sinusoid and then evaluate it for given initial angle and angular velocity. According to Prony's method, first of all, we set up and solve the system of equations to find the predictor. For 2 unknown predictor coefficients, the solution will look like this. Then we get the polynomial with predictor coefficients and find its roots. Considering that we have quadratic equation, the roots s1 and s2 can be written in the following way. Since the sequence of derivatives is real, we have complex conjugate roots and can use only s1 for frequency omega and damping factor alpha. Finally, we can solve the next system of equations with respect to h and separate h into initial amplitude a and angle theta. So now let us evaluate the solution using initial points. At the bottom of the arc, when angle equals 0, we get the following expression, which is exactly the same as we saw before. However, if initial angular velocity equals 0, we get this one, which is somewhat different. We still have a simple harmonic motion, but with one more term for the frequency. Square root of sine theta 0 divided by theta 0. The reason for that is that in this point the function theta changes, but doing small angle approximation, we normally neglect these changes. We just solve the equation for the bottom point, where angle equals 0, and extrapolate this to all other points. It is also possible to consider the solution we obtained with Prony's expansion as a small angle approximation as well. And I would say this approximation looks better compared to that we normally get substituting sine of theta with theta. The first reason for that is that this approximation gives an exact solution of the equation at the starting point. The second reason is that this approximation seems generally more accurate. The third reason is that it shows that period of the motion actually does depend on starting angle, though to a very small extent when the starting angle approaches zero. What do you think about this approximation? It would be very nice to know. If we evaluate frequency omega as a function of time for small angles, we will get something like this. The frequency constantly and periodically changes in a narrow range that makes possible to approximate it with a constant. Let us have a look at how this frequency function looks for a large angle. In this case, the frequency range is much wider. There are regions where the damped sinusoid behaves like a zero-frequency exponential. The solutions we have for the 2 points cannot be used as global approximations anymore. However, they still work locally, near their respective points. Evaluating the frequency omega on the phase plane gives the following surface. We can see that the frequency is close for small angles, regardless of velocity. However, for large angles, the contribution of velocity increases. Prony expansion offers a general approach that can be applied similarly to other differential equations. Say if we have a bit more complex equation with a resistant term, we still easily can get small angle approximations using the same routine. For zero initial velocity, this yields a beautiful solution. That's all for this part of the video. Thank you very much for watching.